So the next speaker is, if I get it right, Antoine Rignon-Bret, who will talk about second law from the Noether current on null hypersurfaces. Yes, please, the floor is yours.
First, I'd like to thank the organizer for this very nice conference and for giving me the opportunity to talk here. So today I will talk about the second law from the Noether current on null hypersurfaces. And the question I want to address today is based on the seminal work of Wald and Ayer and Wald, who showed that in the case of a stationary black hole, the Noether charge, the entropy was given by the Noether charge associated to the null killing horizon. They were in fact able to relate the ADM charges at infinity with the charges, the charge on the horizon in the presence of a background killing field. But what about the dynamical case? Because we know that satisfying the first law is not sufficient to have a well-defined notion of entropy. We also need some balance law, and which shows that for a closed system, at least the entropy increases and is positive. And we know that I wanted to ask if this is possible to find this construction for Noether charge associated to some null diffeomorphism in general. Also, you know that you can compute the Noether charge on very general null hypersurface. And these Noether charges satisfy similar properties as the entropy. So first, before coming to the heart of the matter, we have to review the construction of the Noether charge and the balance law. So first, we have some theory described by some Lagrangian L. We know that when we take the variation of this Lagrangian, we have a sum of two terms, the equation of motions plus boundary term that is a symplectic potential, and from this symplectic potential in the Lagrangian we can deduce some Noether current Xi, and that is conserved if two conditions are satisfied. The first one is the on-shell condition, so the equation of motion should be satisfied, and the second one is that if there are some background field chi, the diffeomorphism Xi should be a symmetry of this background. So we can just think, for instance, a very simple example of the background being the metric, and then the diffeomorphism should be a killing field that act on this this metric. So from this from the previous formula, we can actually integrate it on a finite region of space-time M, comprised of two space-like hypersurfaces and null or time-like boundary. And then we get the variation of the Noether charge on these space-like superficies given by a sum of two terms. The first one is a symplectic flux through the boundary n, and the second one is a term that appears actually when the equation of motion are not satisfied, and it really means that we missed some degrees of freedom. If they are not satisfied, it means that we have missed some degrees of freedom in the description of our system, because here I'm classical, so I assume they should hold, and this is why I call this last term a non-equilibrium term. And to understand how it works, actually, we can apply it to very standard situations. The first one is classical electromagnetism in general space-time with the killing vector Xi. So we see that in that case, if there is some time-like killing vector, the Noether charge will be the electromagnetic energy, and we know that the variation of electromagnetic energy between two space-like slices is given by the flux of the pointing vector on the surface n, on the boundary n, plus a term that appears if the vacuum Maxwell equations are not satisfied, because we have missed the degrees of freedom of the charged matter that can interact and exchange energy with the electromagnetic field. For gravity, this is similar if you have a diffeomorphism invariant theory, except that here we know that the Noether charge is on shell actually a surface charge, and then we have exactly the same results. So the variation of the Noether charge is given by a symplectic flux plus the stress energy tensor that is that appears if the Einstein equations are not satisfied in vacuum, because we have some matter then. And if the null hypersurface is null, and if the null energy conditions are satisfied, actually this term is positive, and this is very analogous, you know, to the usual balance law for entropy, where you know that the entropy variation is given by flux term, heat flux term, plus an entropy creation term that is positive. So here, of course, this entropy creation term is analogous to this T mu nu, psi mu and u for psi being the null future pointing null vector on the null hypersurface. So from this, what we can do now is we want to compute some Noether charges for our gravity. So we start from general relativity, and we have to take some symplectic potential in order to compute the charge. How do we choose it? So first, we have to restrict ourselves to some phase space in order to kill some gauge redundancy. And by doing this, we have also to restrict ourselves to the diffeomorphisms which preserve these gauge restrictions. And the Weil supertranslations that I wrote here, where the general Weil supertranslation is given by a factor W times VdV, or dV is the null vector that, and V is the affine coordinate, is one of these symmetry diffeomorphisms that preserves these phase space restrictions. And then the symplectic potential that we get here is actually in the form P delta Q, is Q variant, with Q being the configuration variable here, which is the metric, and I call it D like Dirichlet because you know this is just, it vanishes when we impose the Dirichlet boundary conditions on the null hypersurface. So from it we can compute the charge, and from the charge we can use the formulas on the previous slide to compute the charge variation, the balance law equations. And an interesting case is when we apply actually this balance law to perturbed Killing horizons, the symplectic flux turns out to be of second order. If psi now is the perturbed Killing field, I mean the background Killing field, sorry, that is actually a Weil supertranslation. And we see that because this axi theta is of second order, the charge variation is entirely given by the flux of matter crossing the horizons, which is a linear combination of the Killing energy, the Killing angular momentum, and the electric charge. And that's, by identification, should be proportional to the entropy variations. But the surprise here is that the little surprise that the entropy is given, there is this additional term in the definition of the entropy, which is proportional to the derivative of the area. And actually it may surprising at front because we know that the first law works when the entropy is the Einstein-Hawking, Berkelstein-Hawking entropy. But we should keep in mind that this formula of the first law actually works in phase space between two equilibrium solutions in phase space. While here we are not really at equilibrium because we perturbed the black hole with some incoming matter. So it means that this first law actually is closer to the physical process first law than the equilibrium process first law. And you know that when you derive the PPFL, the physical process first law, you have to integrate at some point between infinity and the bifurcation surface. And only if you do that, you get that the entropy variation is given by the area variation. But if you don't, you get this local definition and dynamical definition of entropy, and you have this local and version of the first law. So this is good, but we still have issues with this Dirichlet dynamic potential because, as we said, first of all, the first law actually, as I said, works only between equilibrium state in usual thermodynamics, but also we want that an entropy that increase in time, and this Dirichlet entropy actually increases in time and is positive at first and second order in perturbation around the background Killing field, but not at the early stage of the collapse. So how do we change our definitions of the Noether charge to get something that might be better? There is no many choices actually. If we start from the Dirichlet symplectic potential, the only thing that we can do to have another covariant symplectic potential is make an integration by part in field space. And we have new charges associated to the Weil supertranslations, which are very similar to the Dirichlet one, except that there is now a 1 divided by d minus 2 in front of this expansion. And from this, we can calculate the charge variation associated to this Dirichlet supertranslations with diffeomorphisms that here is the Weil supertranslation normalized to W equals 1 for simplicity. And you find these equations, 6, 7, that, this is one equation, that actually, which is interesting here, is that the last term is positive, is the energy condition unsatisfied. The second term, the shear squared term, is always positive, and the first term is positive if the expansion is positive and smaller than d minus 2. And actually, we can prove theorems from this. We can prove that if n is the general null hypersurface, that it has topology B times R. It means where B is some compact space. It means that the null geodesics cross the compact space only once. And if it is future complete, which is mean that we can take the affine parameter V to infinity, if we take some Weig transformation, super translation that vanishes on S for any cross-section S2 and S1, such that S1 is in the future of S, S2 is in the future of S1, the variation of the Weil charge, super translation charge for the York charge is positive, and the charge is positive in general. And if we normalize the killing, it's not a killing, sorry, the null diffeomorphism to be 2p times n, we see that we recover something that is very similar to the Dirichlet entropy, but with now this same 1 over d minus 2 correction in front of the dynamical term. And now, rather than stating the theorem 4, I will just show you the picture because I think it's more enlightening. If we use this new entropy for a spherical symmetric collapse, because earlier with the first theorem, we restricted ourselves to surface with the topology B times R, but we know that event horizons in general have caustics. This is the case even in the simplest case, which is the spherical symmetric collapse, where there is one caustic, where the generators enter the horizons. You can prove that actually this entropy York vanishes on the light cone phase. This is the first stage of the collapse. Before that, matter enters the horizons. Then some matter enters the horizon, and then you can show that if matter at shears enter the horizon, the variation of this charge is positive. And at the end, the last stage of the collapse, it stabilizes to the value, usual value A over 4G. So actually this, when we show that the area is the entropy, it increases even at the beginning of the collapse when no matter has entered the horizon, while with this dynamical charge it does not, because its variation is given by the amount of matter and the gravitational degrees of freedom which propagate into the horizons. And actually there is a nice analogy with the phase transition where the order parameter is actually here the expansions, because the expansions at the beginning is d minus 2, while it vanishes on the stationary event horizon, and this corresponds to an enlargement of the symmetry groups where we recover the super translations that were symmetries of the stationary black hole, as Hawking, Perry, and Strominger was stating. And so I think I'm over time, so I just leave you with the summary, and thank you very much for your attention.
Thank you very much for giving the last talk in this session, and now we have some time for questions. Yeah.
Thanks for the nice talk. So you applied that to black holes. Could you also apply it to the cosmological horizon, like in the sitter?
No, I never thought about this. The horizons, for now only on horizons. Thank you very much.
Are there any more questions? Okay, I don't see. Sorry.
Could you comment more on the York boundary condition versus the Dirichlet? Like,
yeah.
One is like you fix the temperature, and so on. Do you have a thermodynamical interpretation?
Here, not really, because it's so I should precise. Maybe I haven't said it during the talk, but so for the York boundary conditions, the configuration variables are the conformal matrix and the expansions. And yes, no, I don't. It's very. What happens actually that I didn't have the time to talk about this, but we see that it's when you have the Dirichlet entropy, you satisfy the first law locally, and when you have the York boundary conditions, you have an additional term because it cannot satisfy, which is a kind of dynamical term that is proportional to the area, the product of the area and the expansion. I wanted to give at some point the interpretation of this term as a surface tension term, but actually I think it didn't work, or so.
I'm sorry, I have to interrupt you.
Yeah.
This was orders from higher force. So let's postpone this discussion till the coffee break after the discussion, the roundtable discussion, and let's thank all the speakers in this session again for very nice and compact talks. And I would like